us here. Rob, have you attended any of those? What is your, and if so, what's your feeling on how well they work?
I personally haven't. Some of my group members have. I've been mostly caught up with virtual program reviews, which have maybe a similar sort of flavor of, so kind of like a workshop kind of feeling. And those actually seem to work out reasonably well. With some workshops in the past, and certainly with things like program reviews, it's always nice to bring demos. So that's of course lacking. But we've gotten fairly good over the years, all of us, at taking high quality videos and imagery of our work. So I think that that's a decent substitute for these times.
Mm-hmm.
Have you been in any of these, Rob?
I did go to some on Sunday, and yeah, they seem to work pretty well. I think basically you're lecturing. It's 20-minute, half-hour lecture, so that works fine. The questions work okay, as you say. No demos. Yeah. We're supposed to have a workshop or a tutorial at ICRA, which had a big hands-on component. We're going to show people how to make jamming elements, and so we just canceled because without the ability to do hands-on, it just didn't make sense to hold the workshop. So yeah, we'll reapply at some date in the future. Who knows what that will be. Yeah. And how is work going for your group these days with the inability to access our labs? I don't know about the universities where Sulin and Tang are located, but we have been closed. Next Monday, we may reopen for the first time.
Same here. We're closed. We'll probably close. We'll probably reopen in different stages, stage-wise.
Yeah.
Yeah, that's I guess different universities using different terms, and stages were in phases. So we're currently in phase 0 and preparing for phase 1. Currently still closed the labs. Actually, I remember I had some discussions with other people the other day. It's one of the group in another institution, they actually doing some robotics. Some of the equipment they allow the student to bring home, or graduate student postdoc, they can do some limited experiment at home. Mm-hmm. And the postdoc, they are actually motivated to do things. I think that's another approach.
Yeah, sure. Yeah, we were allowed to do a little of that, but I think if you do anything that involves chemistry, serious equipment, you're closed. So it's
the group is obviously quite anxious to get back in. There's the numbers that have been described of 20% of normal density. That actually seems like it would be pretty good. I mean, just thinking about the duty cycle of actual sort of hands-on, experimental work in lab is probably far lower than that as it is. They're spending a lot of times on analysis and coding and just socializing, which of course is unfortunately going to be, put aside. But I think it'll work out pretty well. I'm blown away by the amount of effort and enthusiasm that has been poured into all of the planning for safely reopening labs. It's remarkable, and it's heartening, and I think it shows the eagerness that we all have to get back in lab.
Yes, it's a lot of smart people working very hard on something I hope we never use again. But we'll see. What's the new normal? Who knows at this point? Yeah. Okay. So Rob, you're going to talk about artificial intelligence today as the title. Is the focus, what's the term, mechanical intelligence, adapting the mechanical structures so that they perform what are traditionally information processing tasks?
Yeah, this title that I had is a solution to a problem that I had a couple years ago, and the problem was, how would I describe what we do and why we do it to both technical and lay audiences? And some of these terms that you were using about all these sort of jargon, smart materials or mechanical intelligence or computational morphology or morphological computation or whatever. I don't really know what any of those things mean. And so my former student, Peter Whitney, who's now at Northeastern, he coined this term, and he actually sort of split the robotics universe into two. And he said that the one side of the robotics universe is AI, as we sort of maybe classically think about it. And, I'll do some simple definitions of this later, and that's sort of that's the antithesis of what we do. Like, we don't do that, but we put a lot of effort into hardware designs, which hopefully mesh well with AI type techniques and maybe alleviate some challenges just by virtue of how they're built or how they're designed. So that's what I'm talking about.
Great. Yeah, it's interesting. I think this is actually an old idea that people who design jet fighters, for instance, have long said you have to design the mechanical plant, the aerodynamics, the structural, so that it behaves the way you want it to behave. And then you close control loops, sensors, computers, actuators around it. And if you do both of those really well, you might get the performance you want. But that lesson hasn't been portable. For the first few decades of robotics research, the brains and the body didn't talk to each other, by and large. So this is a pregnant idea. I think it will give birth to a lot of important progress in the field. You've been, I won't say forced, you have come up with a lot of novel ways of building things at interesting spatial scales that aren't available using conventional techniques. And I think most people would have viewed that as an insurmountable hurdle and gone someplace else. But instead, you've actually thought of interesting new ways of building stuff. Can you say a few words about how that came about? How did you figure out the materials and the processes to make that happen?
I think it was out of my own ignorance. I think I've always been a sort of hands-on kind of engineer, and I always want to build stuff. And but that said, I'm trained as an electrical engineer, and so I kind of grew up academically in a MEMSy kind of environment, maybe, where I never really studied any of those sort of techniques, and certainly didn't understand the materials aspect and some of the all the IC derived manufacturing techniques, etc. So I didn't know what was sort of feasible or infeasible at the time, and just started trying things. And some of the techniques that we started playing around with worked out pretty well. And then it's just off of the creativity of the graduate students. I mean, getting people in the group who, once we build sort of one thing that has interesting aspects, like a little robot that flaps its wings or whatever, that's okay, that's exciting. We can sort of get behind that. But the way that you just did that took you, a month to build, and and it works once, and it was, et cetera, it has all sorts of issues with it. So that forced us to sort of refine these techniques. And now actually they're at a point where, a good engineer can walk off the street and just follow a recipe and build something like this. So I think it has paid off quite a bit just to have that suite of capabilities. Now we're a group that's sort of a hammer looking for a nail, because we can build these little robots. That's fine. What are they good for? Well, we can talk about that, but what else, what are more practical systems in which these techniques could be applied to? And that's something we're very interested in exploring. And I think it's, forums like this, maybe, is full of people much brighter than I am, can sort of lob out some ideas of things that we might want to build in the future. That would be great.
Yeah, and the results are certainly spectacular. I'm looking forward to today's latest installment of all that. Since this is a mechanics forum, can you say a few words about materials? So you integrate a crazy array of materials, actuators, sensors, structures, everything. And it seems that the components have multiple functions. They're both an actuator and a structure, the frame. They're both a sensor and a controller. So how does that come about? That's a double challenge.
Yeah, I find that, well, I think that one of the things that was the genesis of this sort of, I'll say efficiency maybe, is the fact that we were targeting small flying things. And flying things at any physical scale is energetically expensive. As you get smaller and smaller, it gets more and more inefficient, if you will. And you have to rely on other mechanisms and other, fluid mechanics phenomena, et cetera. But so that forced us to not be wasteful with any of the things that we're thinking about for putting on this. Has to be sort of monolithically integrated within the device. Has to be, if we can do things akin to measuring back EMF or motor current and guessing torques at larger scale electromagnetic motors, we want to do some similar things with whatever the actuators we're using, piezoelectric, whatever the actuators we're using at small scales, et cetera. And so I think it sort of grew out of, we got lucky in choosing the sort of the first goal of this or output of this. And that has sort of fed into this sort of, multifunctional, multi-use kind of mindset.
Yeah, got it. I can see that necessity drives invention in that case, but the results are very, very intriguing. Things that I don't think are where I might have thought of going anyway to start with. You mentioned that you're starting to look at applications for these technologies. I know you're going to talk about some of them today. Are there some others that aren't in your talk that look promising or that you've previously produced?
Yeah, and I think you saw this recently, Rob, and Peter York's thesis defense. So I think we're, one question that we've posed to ourselves for the past decade is, well, if you can build little things that fly and they're this big or whatever, that have embedded sensors and actuators and control systems or whatever, what else could you build using these same techniques? And the most obvious thing are small scale medical devices, right? So but that said, we've done some exploration, but it's all preliminary at this point. We've done a lot of discussions with with people in the med schools and a lot of talking to a lot of instrument manufacturers and et cetera. I don't think we have the killer app yet, but we do have several drawers full of prototypes of laparoscopic tools and endoscopic tools. And the thing that I was alluding to that one of my students just completed was a laser steering mechanism for GI ablations, steerable GI ablations. So there's all these ideas, but it hasn't. None of them has matured yet, and I think that's partially because of, again, my ignorance of the medical field and what it takes to actually bring something beyond a lab demonstration to actual use, and that sort of long time scale.
Yeah.
We have Rob. Let me introduce our co-editor-in-chief, Jimmy Xia. Jimmy, please raise your hand, Jimmy. And,
hi, Rob and Rob.
So
thank you very much for doing this.
Yeah, introduce I guess somebody Metin City.
Metin, very well. Hi, Metin.
Hi, Metin.
How are you?
Good.
He is also an editor of EML. So Rob, you're obligated to A, promote EML, B, submit paper to EML.
Well, I have a collaborator who could help with that. His name is Zhigang Suo, and maybe he will help me write a paper that I could submit to EML.
That also counts.
Good.
Yep. Rob, actually, we can start now.
Okay.
Rob Wood, please turn on, share your screen. And Rob Howe, please introduce.
Beautiful. Okay, so I'm Rob Howe, and I'm Rob Wood's colleague at Harvard for a number of years now. And it's really been a pleasure working with Rob. I think of him as the guy who can build things nobody else can build. He works at this scale often, which is too big for MEMS and too small for manual machining in our usual machine construction techniques. And so he's been forced to invent a whole technology for fabrication at that scale, which has reached an amazing level of sophistication. I'm looking to hear about the latest today. It's also forced him to integrate actuation, sensing, controls. All these parts serve multiple functions, use unique materials combined in unique ways. And the results are quite spectacular, as we'll see. And let me just add, as Rob's colleague at Harvard, that something the rest of the world doesn't get to see is that he is an amazing individual, everyone's favorite colleague. He's won awards for mentoring, for being the nicest guy working with our staff in the School of Engineering at Harvard. And so he is great in his public persona, as we'll hear, and he's also great to have as a colleague. With that, let me turn it over to him, talking about mechanics and artificial intelligence. Rob.
Thank you so much, Rob, and I really appreciate the kind words. I will note that as I was thinking about this morning, it was about 15 years ago, in a month or two and change, that I got a call from Rob when I was sitting in the lab at Berkeley, saying, "Hey, your interview went well. We want you to come to Harvard," and started talking me through all of the details of the school and the colleagues and all of that. And so I appreciate your mentorship and friendship over the past 15 plus years now. And thank you to Zhigong and colleagues at EML for inviting me for this. I'm very excited to present some of our recent work. And this is, we were just discussing this, but this term, the mechanical side of artificial intelligence, I'll try to define this in a minute, but what this means is, what this sort of came out of was a discussion with one of my former students, Peter Whitney, who's now at Northeastern. He sort of split the world of robotics into two things. One side was artificial intelligence as we sort of classically think about it, and the other side is sort of everything else, the hardware side. And he called that the sort of mechanical, and it has a number of names that I'll get into in a minute, but he sort of coined this term, the mechanical side of artificial intelligence. And I'll try to describe what it means in words. And then I'll try to, the best way I can think about how to tell you about some of the work that we're doing is by example. So I'll dive into a few examples of some of the things that we're doing, and that'll be the majority of this discussion. So artificial intelligence, as we might sort of classically think about it, is the development of systems that are able to perform human-like qualities of perception, control, autonomy, things that normally require human-level intelligence. In natural environments, unstructured environments, decision making, etc. This is what we sort of classically think about as artificial intelligence, and this was coined. This is an old term now. This is over 60 years old now, and coined by somebody at MIT. What I'll say is the mechanical side of artificial intelligence is sort of has some related themes, but it's more hardware focused. So developing platforms, new robots that make some of these challenges for perception, control, autonomy easier or more robust or more repeatable for operation in unstructured, natural environments, just by virtue of how we make them, how we design them, how we build them, the materials that go into them. There's a number of names perhaps for this that I won't sort of dive into all this sort of variance, but embodied intelligence and morphological computation, all of that. So all similar things, and I will make the argument. I probably won't have time to get too deep into this, but historically, this concept I would argue is several hundred years old, and this goes back, to sort of artisanal tool development and sort of early days of mechanism design and construction, where there was no computation of any sort of contemporary view, but they could still develop mechanisms that could do really fascinating things. So anyways, so that's it's perhaps a bit of an older concept than AI as we now think about it. So like I said, I'm going to illustrate the way that we think about these topics through 3 examples. And so the first one is going to be on our sort of small scale robots. So some of this will be a bit old, but I'll include a bunch of new stuff, recent stuff, along the lines of creating small flying robots and small legged robots. And then the last 2 examples will be in the area of soft robotics, which I'll also try to give a little bit of an overview of what that area is and what it means, what it can do, and where it's going. But there will be 2 examples that I'll bring up that are associated with soft robots for manipulation and questions about sort of future looking, could we make entirely soft robots? So the first is robotic insects. So we set out, well, this goes back to my PhD now, and Metin was also involved in this project, quite a while ago when we were both at Berkeley, where the idea that our advisor at the time, Ron Fearing, set out to build a small flapping wing device that could sustain flight and be sort of similar in scale and features and flight capacity to an insect, to a fly, or in this case, I call this a robo-bee, but that's a bit of a misnomer because it's supposed to also sort of invoke some of the social insect aspects that would go into future programming considerations for swarms of these things. But if we wanted to create something like that, then we had to sort of, and here's maybe a vision for this, and I won't really talk much about what these might be used for. In reality, we are excited about these kind of topics because they are very difficult and they require you to sort of think through system level questions that go from, which I'll talk a little bit about, from materials and manufacturing through sensors and actuators to fluid mechanics, to control dynamics and control systems, to programming aspects, energy, etc. So it's these sort of umbrella projects which are inherently very, very multidisciplinary. So that's what gets us excited, but you can envision scenarios for these things being used for example, assisted agriculture or search and rescue or other related topics. So I won't talk too much about that. What I do want to dive into and sort of spend a slide each or so on what are the challenges that are associated with building something like this. And the first is the actual building something like this. So, the very first thing that we started to explore was, well, how would I create something that has feature sizes that range, like an insect, the feature sizes that might range from centimeter-ish down to, tens to hundreds of microns in sort of characteristic dimensions. And I would argue that this is not the way you'd want to do it. This is a drawing of an internal combustion engine from a Ducati motorcycle, thousands of irregularly shaped components, 3-dimensional components assembled by hand, etc. These types of, this is what not to do. These types of techniques, of course, will not scale down. So, and this is a bit of a contradiction of what I just said. This is how we used to do these things. This was now probably 10 years ago, where you'd have a graduate student who would be sort of painstakingly assembling individual components. And I'll show you in a moment how these individual components are made, or talk about how they're made. But under a microscope, tremendous dexterity and patience involved. This is also this sort of process is also called the graduate student with tweezers process, and it's frankly not very good for graduate student retention. Let alone that it's also takes forever to do and build up the skill to do this, and the precision, the yield, all of these things are not sort of satisfactory. It did yield successful devices and allowed us to sort of make some progress, but it was clearly a pain point that we needed to alleviate. And so we looked at this is a rough quote, approximate quote from Nobel laureate Richard Feynman, and he had a famous speech a number of years ago where he described, it's called Plenty of Room at the Bottom, where he sort of prophesized about solutions to some of these challenges in millimeter or sub-millimeter scale mechanisms and robots. And he described, basically the sort of economies of scale you can get at small scales where you have, let's say, robot hands building replicas of each other. And so sort of multiplying in that regard. He talked about, again, the economies of scale with respect to, operations that could be massively parallelized by virtue of the sort of features of these small scale systems that he was envisioning. So we took some inspiration from this, and we also took inspiration from other places too, in particular folding-based assembly methods to sort of start to alleviate some of the challenges of some of the more manual operations I was showing in the previous video. So they took a lot of inspiration from, you know, origami or kirigami. It took a lot of inspiration from things like pop-up books, where you have, you know, sort of single degree of freedom mechanisms that are controlled by a single point, pushing or pulling or unfolding or whatever, where all of the sort of assembly associated with, you know, putting a wing here and an actuator here is done by virtue of the design of the parallel mechanisms built within the thickness of this device. Now, I haven't showed you how this device is made. I won't have time to get too much into this. Here, I'll show you this video and sort of the real thing. But this is something which is made in a sort of nominally two-dimensional pattern. We do bulk micromachining of thin materials, and these materials can be really anything. Polymers, ceramics, composites, metals, doesn't really matter. We use UV lasers to bulk micromachine each individual layer. We also laser micromachine freestanding thin film adhesives that we lay up in using persistent pin alignments, and then laminate together to get the device you just showed, which is then sort of folded out of plane in a pop-up book-like assembly process. Goes through some fixation steps, and then is sort of, you know, removed from the assembly scaffold, throw away the scrap, and then you're left with this kind of device. So we call this technique pop-up book MEMS, and it's able to allow us to create. It has a number of nice features. It allows us to create things in sort of fairly rapidly if the designs are done. I'll come back to that in a moment. It allows us to sort of, you know, create things in parallel. We can create large numbers of things. Sort of large for us, by the way, is a few. We can create relatively large numbers of things. We can create, and this is provable, that we can create any three-dimensional object by virtue of these techniques, and any object with any sort of articulation. The articulation in these devices is based upon gaps in rigid materials that expose a flexible material, typically something like polyamide or other similarly resilient polymers. And so these are based on flexure hinges, and so these flexure hinges allow us to do not just the folding for assembly, but any sort of motion that we might want. So the flapping of a wing, for example, is controlled now, and I'll get into the actuation a little bit later, but is controlled by this piezoelectric bimorph bending actuator, which we create in the same sort of laminated process. But now what's happening here is you can see the sort of motion of this small actuator is being amplified by something you can't quite see. There's a parallel 4-bar mechanism, a crank slider mechanism, which is converting that relatively small motion into a large flapping motion. And you know, coming back to the original sort of thesis that I wanted to present in this discussion of using the sort of design of this device to try and alleviate some of the challenges sort of down the road. I'll show you in a few moments that when I plug these in and try to fly them, they're extremely unstable. And so having active control is absolutely necessary. And we worked at the genesis of this project, we worked with biologists who were studying insect flight, Michael Dickinson and his colleagues, who at the time was at UC Berkeley. And they were describing some of the principles behind how these things operate, how insects operate, meaning they sort of abstracted all the sort of details down to having a 2 degree of freedom motion, where you have sort of a flapping motion and a simultaneous rotation about an axis roughly parallel with the span-wise direction of the wing. So you get these sort of treading water motions. And our initial attempts were sort of naively to try to recreate that, you know, 2 degree of freedom system as a 2 input, 2 output system, 2 actuators driving 2 rotational modes. And that turns out for a system like this, where we want, for efficiency reasons, to drive that at the resonance of this flapping structure, turns out to be rather inefficient because of coupling. You're always going to be putting energy into fighting modes in the system. So we let's see. So we were able to come up with methods that would allow us to sort of create. And I'm just showing this now. As a sort of more complex example of the previous device that I just showed you. So if I just sort of go back to this for a second, I don't think I made my main point, which was this sort of 2 degree of freedom motion that we wanted to achieve failed when we thought about it as sort of commanding those two motions sort of explicitly, or directly. Whereas in this device, what we can do is have a passive mode. So this rotational mode is passive. And just by controlling the stiffness of the flexure hinge that connects to the wing and the inertial properties of the wing, we can put that mode much higher than the flapping resonant mode. And so we can have sort of quasi-steady operation of that sort of rotational mode, and there's a whole bunch of nuances here that make this really, that make this sort of really important to get some of the details right. Like if the phasing between these two modes is incorrect, you're going to get negative lift, and so obviously you don't want that. So we can make variants of these sort of mechanisms, and I'm really only showing these couple slides just to show the sorts of complexities that we can achieve using the techniques that I sort of showed you before. So let's see. So this particular mechanism is based upon, I'm not going to recall all of the details here, but two parallel 5-bar mechanisms, 2 parallel 4-bar mechanisms, and 2 planar 4-bar mechanisms sort of packed into a device, which is a few cubic millimeters in size, or let's say a cubic centimeter in size, and we sort of zoom in to see the sorts of complexities that we can achieve here. And again, this is all just based upon these lamination and folding sorts of techniques to be able to create these articulated mechanisms. You can kind of see in here, like here's a flexure mechanism. I assume everybody can see my pointer. Let's see, and then more sort of rigid links that are based upon these, in this case, fiber reinforced composite materials. Let's see, and what else do I want to say here? I guess that's probably it. But we can make these really elaborate mechanisms using some of these techniques. So the next question that we had was regarding controls. So jumping ahead a bit, we tried to to think about separating the questions about the sort of control algorithms that we might have or might want to have from the actual hardware that's going to implement them. And specifically what I mean is, we sort of set up this environment where we have training wheels, effectively training wheels, where we have this sort of motion capture environment with cameras that are sort of around a flight volume. And this is a very typical setting that you might have in for motion capture for larger scale drones or a whole bunch of other robotics activities. But the interesting difference here is that, of course, that it's scaled way down. We're talking about maybe a cubic foot of volume in which we're flying in. And so that allowed us, and what's not depicted here are sort of banks of computers that can be implementing whatever sort of control mechanism that you want. Here's the setup that we have. Here's the device in question. So this, through some extensive tweaking, et cetera, we're able to get pretty good, real-time, feedback, with latencies on the order of, 10-ish to maybe 10 to 20 milliseconds, or maybe even less than that, which allows us to do real-time state estimation off-board and allows us to write controllers that can stabilize flight. So that's a huge tool for us to, again, allow us to separate out these questions of algorithmic side of control from the sort of implementation side of control. And so this is what happens if I just sort of set these things down and press go. Open loop, they're very unstable. This is notably this is slowed down by a factor of 8. So this is in real time now. And what's happening, what you're seeing here is just a sequence of sort of training flights where we are sort of learning some of the dynamics associated with these devices. We model these, we simulate these things, but in the end, we put a lot of effort into fabricating things repeatedly. But at the end of the day, of course, there's fabrication errors that creep up, there's defects, et cetera. And so given the unstable, open loop unstable nature of these types of devices, which is the same for their insect counterparts as well, in the absence of active feedback control, they fall. And so this is what happens if you get the control system correct. This is just simple hovering, and hovering might seem very simple, and indeed it is. But going back to this thesis, the use of hovering as a demonstration here is strategic because in the absence of forward velocity, there is no mechanism, I save one, that we could sort of employ in this to get passive stability. You know, it's unlike a sort of fixed wing aircraft where we could have, for example, a positive dihedral on the wings. And, you know, if the pilot removes his or her hands from the controls, then, you know, the airplane, you know, assumes a stable configuration and does not plummet. In this case, you know, we have no such mechanisms that we can employ. Again, there is one exception, but it's applying sort of aerodynamic dampers to the things, and I'm not going to talk about that today. But so we chose hovering just to sort of illustrate some of the challenges associated with trying to achieve stable flight. But we could go beyond that, and so over the course of the years, we've done a bunch of sort of fun experiments, now actually getting into the algorithmic side of controls that is enabled by the fact that we can build these platforms. One of the other things that you will probably note is that, not in this video, but in the previous ones, these things crash. For the most of times, maybe not so much these days, but most in the early days of these experiments, we didn't bother to sort of try to land them softly. We just turned them off and they crash. And this is just due to simple physics of scaling arguments that these devices, you know, dealing with things at these scales is a real pain, of course, to build and design, et cetera. But we do get some wins. And this is one win. They tend to be more robust, you know, at these physical scales than let's say, you know, a larger scale quad rotor would be. You certainly wouldn't want to crash that. You certainly wouldn't want to have humans in close proximity with drone experiments. With these ones, there's no big deal with that. This is an example of something called iterative learning control, where this is trial 8. The first 7 trials failed for this aggressive maneuver, but we were able to learn through analyzing the trajectories in the state space for this robot, some unknown dynamics, and then use that to learn better control policies that allow us to do this aggressive maneuver. More recently, last year, if I sort of think about the list of problems that we would have to solve in order to achieve this vision, how do we build them? Okay, great. We have some solutions, some knowledge on that and the associated materials and processing steps. Next one would be, well, how am I going to actuate them? There's no electromagnetic motors off the shelf that would scale to these physical scales and be remotely efficient enough to operate these things. And so I haven't really told you much about that, but they're piezoelectric bending biomorph actuators. We've had a solution for that for a while now. They're okay. They're not perfect. They work well enough. But they have some nuances associated with them. One is that, I guess, somewhat ironically, the vast majority of the weight of these devices is lead, because they're lead-based piezoceramics. But the other one is that they require relatively high voltages to operate, which is a challenge for bringing these things to autonomy. And so what we did over the past couple years is try to address this question of power and power distribution so that we could get rid of the tether, eventually get rid of the tether, which was providing both the power and control signals, which you were seeing in all of those previous videos. And so what we did was we took the characteristics of these piezoelectric actuators, which are kind of not seen here, but you've sort of seen them operate in the past videos. And these are basically they're two parallel plate structures, just 2 parallel plate capacitors that electrically represent the piezoelectric elements in this actuator. And they're just a bending bimorph, so they basically just actuate 180 degrees out of phase and then produce this sort of oscillating motion. But they do this at relatively high voltages, you know, on the order of 100, perhaps to 200 volts. And so we have put some effort also into developing some relatively simple and at this point discrete component versions of some drive electronics. And so what's depicted here is a combination of a boost stage, which takes in this case solar cells operating at a few 3-4 volts. Open circuit does we've done a number of different versions of this, whether it's they're mostly transformer based, auto transformer based, or flyback converter based boost circuits, which can take that up to whatever the voltage rail that you might want, again 100 to 200 volts, and then drive these capacitive elements which represent the plates of the PZT actuators. And so that's done based upon some very simple local feedback on a little microcontroller here, and that allowed us to do some of the first this is the first demonstration of untethered flight, where we have now there's a solar cell that's sort of sticking on top here. It looks kind of unwieldy, but there's a solar panel that's up here. There's a set of lights up here, which are effectively powering this thing. I should note that this is greater than one sun. We're currently trying to operate to get the efficiency of the system, both mechanical, aeromechanical, and electrical, up such that we can fly at one sun, and we think we're pretty close. But this is greater than one sun, but nonetheless shows that we can integrate all of these components, all the electrical components associated with driving. Now, this is also just open loop. We're not doing any feedback control here. And the way that we can get away with that, which is contradicting what I said before about these things being open loop unstable, is that we just messed with the mass distribution here. So it's still unstable, but it's able to have flights long enough where we can sort of prove our point with this. This was on the cover of Nature last year. We can also, this is now, there's a whole bunch of things that we're currently trying to solve with these types of devices, things like refining some of these power circuits. We think we know what sensor information we would need to do reasonable state estimation. And now we're trying to sort of package those things in small enough scales. And then of course, embedded systems questions for how we would actually implement the control. These are things that we're currently working on. But at the same time, since we have these devices, we can also do some fun explorations of it. And one of them is this sort of vision of multimodal locomotion. And if that doesn't make sense, here's a vehicle, and I'll come back to this in a minute. Similar kind of thing, but we realized a few years ago, one of my students realized, this is Kevin Chen, who's now assistant professor at MIT. He was studying some of the fluid mechanics of these devices, and he realized that, well, if you fly these things around in air, and if I now sort of change the fluid to water, and I just slow down my flapping, I get a very similar fluid mechanics. And so what this means is, I didn't mean to stop that. What this means is that we can then have these things, which is hopefully being shown here, we can have these things be swimming around in water. So we can do control of sort of flapping motion in water in a very similar way as we do flapping motion in air, and produce very similar flow structures to produce thrust. And so, okay, well, that's fun. Getting into water, as you just saw, was relatively easy. Getting out is very, very hard. And that's something which is maybe intuitive, that the sort of surface tension forces that are associated with this robot emerging from water are far, far greater than the thrust greater than its weight, and far greater than the thrust that it can produce. And so the same student, what he was able to do is produce an impulsive mechanism whereby there's little electrodes in that vehicle, which then break down through electrolysis water into oxyhydrogen, and then ignite it, and then it just sort of bursts through the water and sort of ready to fly again another day. So that was a fun one. We also did some, again, taking advantage of some of the physics of scaling here, take advantage of electrostatic adhesion to be able to create perching mechanisms. And this is something where we were able to show, so there's some bioinspiration here, which is maybe hidden of how we would think about control strategies for approach. We took some inspiration from some work on researchers who were exploring optical flow guided control strategies for approaching and landing on objects. But nonetheless, there's some interesting things here where we can sort of perch on and take off from natural and artificial substances just using a very simple electroadhesive mechanism. And then I want to switch gears slightly to say that, we realized, of course, that we could potentially, if we can make little flapping things, that we could make little mechanisms that could do other things like legged locomotion. And so we have a platform now that we called Hammer, the Harvard Ambulatory Microrobot, where we can create legged devices, which again, sort of have a lot of bioinspiration. This is a quadruped, although it takes a lot of its sort of dynamical inspiration from insects, cockroaches, etc. And one thing that I think that is nice about this sort of platform, well, a couple things. One is that first, we don't sacrifice complexity as a function of scale. So if I think about a larger robot, an Atlas or a Spot or something like that, and I think about all of its actuated degrees of freedom as maybe a measure of complexity, I would sort of intuitively argue that as I scale such a device down, I'm going to lose some of that complexity just for practical reasons. And Now, with these types of techniques that I showed and sort of described to you earlier, we don't sacrifice that. We can create, mechanisms that have, many degrees of actuated degrees of freedom. We've created, little myriapod inspired things that have, 20 legs and 40 actuators, all in the sort of, few cubic centimeter kind of size ranges. The other thing is that, if you're not flying, these legged systems, of course, have more payload, so you can support more other systems here. And so these are fully autonomous now, where we can have power control communication systems all embedded within these. And you can do other fun things with these devices. One is, sort of gate studies. These aren't showing any particularly useful locomotion mode, but they're highly energetic. They have payload capacities in excess, in some instances, up to 10 times their body weight. And so they can do rather energetic things. The other thing is that we can, again, take advantage of physics of scaling and have mechanisms by which we can adhere to various surfaces. And so this is work we did with Rolls-Royce. They had an interesting value proposition to say, we want something to go deep inside jet engines and inspect for cracks or defects. And the value proposition was that, if you don't do this sort of remotely, I guess, then you have to take the engine off the aircraft every so often, which is a huge expense and time, et cetera. And so, so we further developed this platform to have electroadhesive feet, and just sort of illustrated here. Here's the adhesive pad. This is on a conductive substrate, but we're also simultaneously working on non-conductive substrates, which is much harder. But same sort of robot here, spherical 5-bar mechanism with 2 degrees of freedom, and then there's a passive spherical 6-bar at the ankle, what we call the ankle here, which is allowing for 3 degrees of freedom of rotation at the base of the foot to accommodate for not just the motions of the legs themselves, but also any sort of asperities or surface curvatures, etc. And this is a fancy video where you're supposed to, this thing on the right here, you're supposed to realize that the gravity vector is indeed pointing downwards. So this is inverted locomotion on a metal substrate using these electroadhesive pads. And the nice thing is that we're already operating with high voltages. So the high voltages that we're using in this video are basically the same that we're driving the actuator. So it's no greater sort of electrical complexity than we had with the previous devices. We can do other fun things like, again, multimodal locomotion, where the idea here is we can sort of have these weird looking feet on these devices, and through a combination of sort of passive sort of flapping like paddling motion, and then controlled electrowetting, where we can control the contact angle of water on these electrode surfaces by applying an appropriate electrical field. We can do some simple demonstrations like walking on the surface of a solid land, transitioning to be sort of floating on water, and then through this process of controlled electrowetting, sink, sort of removing those surface tension forces so that we can break the surface of water, and then locomote on the sort of floor on the subsea floor surface using the standard typical gates. Okay, so that was one half of what I want to talk to you about, and I guess I'm going a little bit long here, so I'll try to move a little bit more quickly. What I want to talk to you about next is soft robots for the deep sea. So this is going to be our sort of foray into soft robotics.
Maneuvering for.
And I'm going to let this play, and you can hear what's happening here.
Sorry. No, I'm not sure he's going to swim anymore. By the commentary, there he goes, and it's sideways. He's swimming. I told you he'd swim sideways.
Okay, so the commentary I think is kind of amusing here, but the idea is, the high-level idea is we got involved with some marine biologists who were trying to do some things like you just saw, and also like this. They wanted to go down to the deep oceans and sample creatures that maybe had never been explored before or underexplored. But they were using these sort of, rigid gripping mechanisms that were meant for the oil and gas industry. They're made for the oil and gas industry, and specifically, they're way overpowered for something like this, and their precision is also quite lacking in terms of things like force feedback. And this is bad, right? If you just want to get a sample of this thing, sure, you can just mangle it and grab it and bring it back up. But what you really would want, as I've learned from my colleagues, is you want them in an unstressed state. meaning you don't want gene expression which is sort of unnatural for them for their environment. You want to get them whole and happy. And so in order to do that, we said, oh, well, you know, we're at the time, this is, well, I guess 7 years ago now, we were making these kind of things, which were these very, very simple structures, elastomer bladders that had some fiber reinforcements within them. And based upon the nature of the fiber reinforcement, I could control the motion of these things to create just sort of pure extension or extension bending coupling, extension twisting coupling, bending twisting coupling, whatever. And this again comes back, I think this is one of the primary examples of this sort of thesis of trying to build in complex motions and behaviors, if you can call this a behavior, just by virtue of the design of this thing. And so just by making, you know, these simple, and this on the right is just a, you know, extension bending coupling actuator, we can make, you know, crude examples of anthropomorphic hands that are, there's no control here. All we do is just pressurize. We inflate to a certain pressure, and by virtue of the compliance of the materials and the working fluid, you know, we can have stable grasping on a variety of objects. And furthermore, because we're more sort of impedance matched, if you will, to delicate objects that we might want to grip, then we can do this in a delicate way. And so this got us interested. This is sort of one of the how we got involved in soft robotics. And I think it's, you know, it's this as a sidebar here, and I won't dwell on this, but soft robotics is a very active sort of subfield in robotics over the past decade or so. Started back in the 1980s with a guy named Suzumori in Tokyo, who was building some really fantastic examples of small scale, pneumatically driven, multi-degree of freedom, soft actuators, and then sort of gripping mechanisms and crawling mechanisms. But there was there was other examples over the ensuing years, but this really sort of, I think, in my opinion, sort of started to pick up speed when DARPA had a program called ChemBots, chemical robots, which the idea was, as its name implied, sort of non-traditional soft-bodied robots powered by powered and controlled in interesting ways. And that led to a number of interesting results. Fast forward a little bit, now we have soft robotics as a journal, which is, it was until Science Robotics took over, the highest impact factor journal in all of robotics, which I think says something about the community's interest in these areas. So we took, we got some funding from the National Geographic Society, and took one of my colleagues' remotely operated vehicles, hooked up this soft robotic hand, went over to the Red Sea. This is a recognition to our sponsors, of course. Here's one of the examples of these soft fingers. This is yours truly doing a dive with this robot. But the idea here is that we wanted to go grab objects at the bottom of the ocean, as I said before, but we want to do it gently. And so furthermore, we want to be able to do this robustly. And so you can see this sort of whip coral thing here. And I would pose, for those of you that are interested in into manipulation, I would pose that, you know, if I wanted to do this as a manipulation problem, where I wanted to go robustly grasp this thing, and I'm doing this teleoperated from a ship that's maybe a couple kilometers above, you know, and the boat's rocking, and all I have is 2D visual feedback. And this thing itself is rather compliant and can move around in the current, etc. That's a really challenging problem. So instead, what we did, as you just saw in this video, is just develop an actuator where we can sort of get close enough, and then once you power on this actuator, I get extension twisting coupling, which forms a helix structure, and then just sort of wraps around, gives this thing a hug, and then sort of clips it off. We also made more sort of maybe traditional looking soft manipulators, grabbing this sort of broccoli looking coral device or coral species, and that worked out quite well too. This sort of exploded a bit after we realized, after these first demonstrations, that this was a reasonable approach, and you know, some of the feedback from some of the operators and the marine biologists were that, you know, they were able to grab things that they could never grab before. We took this on other cruises. This is on the Nautilus, where we were able to join a couple of cruises and take this now down to even much greater depths. So down to, in this case, 1,800 meters, and grab these rather alien looking creatures called Holothuria. These are just sea cucumbers. But long story short is that we can grab these things who are, you know, the consistency of these things is, you know, wet tissue paper effectively, but nonetheless we could grab these things, and they were rather, you know, they were rather happy and happy to be picked up and put down. So again, more sort of proof of concept. We could also grab more rigid yet delicate things like this crab, and I'm just going to fast forward here because, you know, he tries to get away and we capture him and all of that.
Oh, don't let me go. Okay, bye now.
Anyways, we can capture a whole bunch of different kinds of animals using these techniques, and that has been quite successful. We also applied these to in another cruise to a manned submersible, where we have now an operator who is wearing a wearable sensing device, which is now an input device, which is controlling the motions of now this whole, not just a gripper, but now a whole arm, a whole compliant arm here, which is sort of composed of multiple segments that can now articulate around in space as well as grasp. And that's then again controlled through teleoperation through this. You can't see it, of course, but one of the operators inside is wearing this device. We also, this is not necessarily soft now, but we also linked up with the Monterey Bay Research Institute and in California, and we're able to get on board one of their ships and pilot a prototype device which looks like this. This is now taking this sort of notion of delicate interactions one step further. This is not a soft device. This is a sort of rigid folding mechanism. But the idea is that if we want to study an animal, and this is perhaps an animal in the water column, rather mobile animal at that, we can just go capture it, never really touch it, although we obviously, you know, angered it because it squirted its ink at us. But do sort of non-contact measurements of whatever it is, morphometrics or chemistry, respiration, whatever, without ever damaging the animal or even touching the animal, perhaps. And this is again coming back to the theme of just sort of being respectful, not just trying to sample, you know, and get things in their natural state, but also being respectful. Some of these creatures, not this one, but some of these coral creatures can grow to be thousands of years old. So we don't want to damage those ecosystems. We also have been taking some of these manipulation concepts a bit further, because while these were effective at sort of grabbing things, that's about all they were good for. I mean, we could grab things, pick them up, and put them down. But we were interested in exploring, not just for this particular application, but for just, you know, general manipulation tasks. Could we use some of these same techniques, but maybe expand them a bit and add more articulation, more degrees of freedom within these devices to have more dexterity for things like in-hand manipulation? And in-hand manipulation is just what you're seeing here. So not just having a stable grasp, but actually being able to manipulate objects within that grasp. And so this is a relatively simple device, which basically just takes that same soft actuator mechanism that I showed you previously and splits it in two. So I have 2 chambers per actuator now. So I get not just a bending motion, but also a sort of lateral motion. And I can control gates to do things like you're seeing here with rotations, etc. If we do something slightly different, we can have now 2 degrees of freedom in series, and have now quite robust things like pinch grasps on very thin or, you know, compliant objects like these sheets of materials here. And this is ongoing work where we're thinking about, you know, what can we grasp and manipulate with these objects. That's one layer. With these soft manipulators, that's one layer. But how can we take this further and enhance the sort of dexterity of these things? And eventually, could these things be appropriate for things like, you know, human type tasks, or, you know, human level dexterity for, you know, household tasks, for example. Oh, and this is just the same thing, but now folding the sheet. So great. So now, other aspects of soft robots, this is just sort of my perspective on what are the current grand challenges in soft robotics. We need analogies to things we take for granted in more traditional, larger scale, rigid robots. And those are just the component level things. So muscle-like actuators, and I'm using sort of human level, sort of skeletal muscle level sort of metrics here to aim for in terms of energy density, bandwidth, efficiency. And ideally, all of these things that I just showed you are fluidically activated, which is fine if you don't care about having a fluidic tether, which was totally fine for our deep sea explorations because the working fluid was seawater, so that was no big deal. But for things where I might not want to have that tether, I think I might want to have something that's electrically activated. For another aspect is skin-like soft sensors. And I'll mention that in a minute. The energy storage I haven't talked about, especially if I'm thinking about electrically driven things, but also for fluidically driven things. Embedded controllers and manufacturing strategies. I'm going to talk about these last three in the last example, but a couple of examples of the things that we're doing along the lines of artificial muscles, electrically activated artificial muscles. We're working with David Clark's group at Harvard and others as well, who are pioneers. You know, Zhigong is one as well, pioneers in the area of making dielectric elastomer actuators super high performance. And where we come in with this is some of our the sort of manufacturing strategies that we've helped develop, which can create devices like this. And it's hard to see this, but each one of these, this looks like it has 20-something layers, but each one of those 20-something layers has 20-something layers in it itself. So this is, you know, hundreds of layers of these sort of parallel plate capacitors with nanotube electrodes that allows us to, and the composition of the elastomer also does not require any sort of pre-stretch, and operates also operates at reasonable voltages. These are relatively high voltages in these videos, but we've gotten actuation down to several hundred volts for some of the actuators that we're developing. So it's really sort of our role is sort of taking these the promise of some of these dielectric elastomer actuators and trying to work through some of the practical challenges. How do we scale up these systems in terms of things like number of layers? How do we scale down voltages by scaling down layer thicknesses? How do we think about you know, different material compositions and you know, things like having not just the right elastomer composition, but having a strain compatible electrode material that's still highly conductive, et cetera. So that's an area which I think is highly promising. Another area that we've been also looking into is wearable soft sensors, skin-like soft sensors. So this is something we've been doing for a while with a few different collaborators at Harvard, with Connor Walsh's group, at MIT, David Newman's group. So we've been looking at this concept of fluid elastomer composites. Is liquid elastomer composites is the sort of typical architecture that we use, and they look kind of like this. This is a bit old now, but the idea here is I've got an elastomer with some microchannels that are filled with a room temperature conductive liquid metal. And by virtue of the sort of design of the geometry of these channels, I can create highly effective sensors, multi-axis sensors, which you can kind of see in this video. I can create normal pressure sensors. I can then create sort of in-plane strain sensors, all with materials, you know, that are sort of limited in terms of their modulus by the elastomer matrix modulus. And there's a whole bunch of nuances of the materials aspects, in particular of the liquid that's chosen here, but I'm not going to get into that. We can also do shear mode sensors and bending sensors using sort of similar deviations from these microchannel geometries. Now, last topic. In the soft robot examples that I showed you, in all of them, whether it was the sort of soft underwater manipulators or if it was the you know, dielectric elastomer based actuators, there's some rigid components in these systems. You know, meaning there's you know, a rigid battery or a pump or an accumulator or a microcontroller or whatever. But they're, you know, typically what we found in our work and other people's work is that you know, the sort of the business end, the end effectors of these things are soft, but the rest of these systems are more traditionally hard, and that's fine. And I think that's appropriate. And I don't think that we want to necessarily have soft robotics sort of take over all of these nuances necessarily. But in an exploration with our colleague Jennifer Lewis at Harvard, we posed the question, you know, could we hypothetically create a robot that is entirely soft? And so that sort of, you know, led to back to these component level questions. And could we make things that are, you know, what are the components that we would need to sort of replace with soft versions? And so we already showed you actuators, I already showed you sensors, so that left us with sort of basic questions in, well, how would we control these things? And let's say a fluidic actuator, how would we control them with a soft controller? And how do we power this if we don't have a pump or some electrical means of generating pressure changes? And so we settled upon a couple we focused on those two components. And the first is power, and we just basically used a monopropellant decomposition, a monopropellant fuel to decompose in the presence of a catalyst and produce basically pressurized gas, which is perfect for downstream fluidic actuators. And then for control systems, we looked to the extremely rich community of microfluidics and devices which were made using soft lithography techniques. And this is what's shown here is a relatively simple structure, which is an oscillator. But it turns out that you can create fluidic analogies of a large percentage of simple electrical circuits, so shift registers, oscillators, I've shown comparators, as well as simple passive components. And this has been known for decades. This is not, that particular revelation is not at all new. But we can use that sort of electrical analogy to start to make now control systems and power systems and assemble them together. And so the architecture that we proposed would look something like this, where I have fuel reservoirs that were fed into, in this case, our microfluidic controller, which is just an oscillator, so it's rather simple, through some check valves into a catalyst site, which decomposes it into pressurized gas and powers downstream actuators. And so that's all well and good. The next question is, how would we make such a device? And this is really where the brilliance of Jennifer's group really sort of blew me away. And they came up with, they at the time, or prior to that, had come up with this concept of embedded 3D printing. And embedded 3D printing, as the name implies, takes a uncured elastomer matrix. What you're seeing here is basically a mold, inverted mold in the shape of this octopus. By the way, this is an octopus because it's this sort of de facto, over the last decade or so, de facto sort of motivation that people cite in soft robotics, or I should say inspiration that they cite in soft robotics, are the high functionality of octopuses, etc. Anyway, so this is an inverted mold with an uncured elastomer, and what you're seeing here is a print head which is injecting a sacrificial ink. This sacrificial ink is a pluronic which does a reverse phase change. So what happens is, after this whole thing is cured, then I've got this sort of this pluronic material, this sacrificial material, which is embedded within the sort of vasculature of this now cured elastomer matrix. And this sort of breaks down into just water, and then that water evaporates through the porous, this is a silicone elastomer, so it evaporates through the porous network of the silicone elastomer matrix. And then the last thing in here, which is maybe hard to see in that, but maybe you can see it better here, within that mold is embedded a little microfluidic chip, which is the sort of control circuit for this device. Again, it's just a simple oscillator circuit. So here's this device. You can kind of see all of this sort of vasculature is this sort of pink lines here, and making behaviors in the soft device. So we've taken that a little bit further more recently with starting to think about going back to some of the multi-layer laminate-based approach and folding-based approaches that we had to creating complex rigid structures. Now we're doing this a bit with soft structures too, just by virtue of a process that we've made to create sort of combine soft lithography, laser-based micromachining, and lamination to create things that can have this sort of microfluidic vasculature now going through vias in individual microfluidic channel layers to other parts of the structure, and then can sort of produce motion by virtue of this. The other interesting nuance of this particular process is that if we first, in some of the channels, flow in a curable elastomer, uncured but curable elastomer, let's say UV cured elastomer, we can actuate this particular device to a particular pose that we might want. Let's say a three-dimensional pose that was formed by folding, and then freeze it just by flashing UV light on it. And now I've got a sort of quasi three-dimensional object, soft object, which can be further manipulated by pressurizing the fluidic lines. And then briefly, since I know I'm out of time, there's a couple of other things that we're doing. Oops. I don't know which one of these videos is making noise here, but just go one by Oh, it's that one. Okay. So so I told you about muscle-like soft actuators. We've done some work with leveraging some of the small-scale robotics that we've made. And I showed you some of the techniques about, related to before, to study things like some odd behaviors in a variety of insects and arthropods, like jumping off the surface of water. We've created 3D printed soft robots. We've created robots that are based more sort of faithfully based upon origami principles that can fold themselves, unfold themselves, form one structure. In this case, again, they're relatively simple, and sort of be a sort of, you know, programmable mechanical device. We've also created origami-based devices which can fold themselves up and then walk away as sort of a self-assembly method. More recently, we're involved in a MURI that is looking at ultra-fast motions in biology and trying to create physical models which can help understand the energetics of these organisms, and then also used for interesting sort of, you know, robotics-like use cases in terms of jumping or punching or striking. So hopefully this gives a decent overview of the types, not just the types of things we're working on, but the sort of, hopefully it was clear, pervasive themes associated with a hardware focus on building devices which can have unique properties, but just by virtue of how they're made, how they're designed, and sort of make some of these questions of control maybe a little bit easier, maybe coming one step closer to sort of merging body and brain within robotic design, as opposed to thinking about them in isolation and then sort of gluing them together. So I thank you for your invitation, for your attention, and Rob and Zhigang, I'm not sure of the format, but I'm happy to stick around and have a discussion.
Yeah. So we'll get Rob.
Should I stop share?
Yeah, stop share.
Okay.
Oh, hey, Rob is here.
Great. Well, maybe I can jump in to ask the first question and abuse my privilege as moderator, and start out by saying what an amazing set of accomplishments these robots do, things I never thought I would see robots do in my lifetime. Let me ask about materials, since this is a mechanics-focused seminar series. So you use a huge range of materials: soft, stiff, actuators, sensors. What do you see as material limits? What do you wish you had in the way of a material that would make building these kind of machines work better?
That's a great question. I mean, there's a couple of things off the top of my head. So we use, for example, in one area of the more rigid small scale robotics work, we use fiber reinforced composites quite a bit, and that's for a couple of reasons. One is that ultra high moduluses, and low densities, so that we can create lightweight stiff structures. But as we shrink these things down, then we're sort of pushing the limits in terms of the physical scale of which they become useful, just due to the sort of discrete nature of the fibers themselves in terms of their physical size. So materials, you know, high modulus, low density materials, maybe that's an obvious one, that are sort of more amorphous and isotropic, maybe. That would be one. We're always on the lookout for electroactive materials. So anything which could be, you know, we like dealing with things that are sort of thin, flat form factors, because that fits well with our sort of quasi two-dimensional machining and lamination approaches. So we're always on the lookout for, you know, for unique high performance electroactive materials. And that could be for sensors or actuators, but mostly I'm thinking about actuation, because actuation is such a really difficult challenge. We'd love to get away from the piezo ceramics because they're brittle and they're relatively high fields, and high densities as well. So you know, those are the first two things that come to mind.
Very good. Okay, let's see. I see we have a question from Tahir Saif.
Yes. Hi. Fascinating talk. Wonderful. Couple of questions. One is related to Bob's question. As things become smaller and smaller, we know that there are friction, adhesion type of issues, and since your devices are three-dimensional, there seems like a lot of assembly involved. Do you see where is the limit particularly from this materials point of view, mechanics and materials point of view, the friction, adhesion, and assembly, is there a limit to the size? And if you think of large scale manufacturing, lots of these devices will be produced. With this 3D assembling manufacturing process, do you see there's a limitation involved?
Yeah, these are great, some great questions. Thank you. In terms of, scaling limits and sort of, friction or tribology issues that might come up. Yes, if you are doing sort of, tab and slot kind of things where you're making 3D structures by, more, let's say, manual approaches, or, like I said, tab and slot or nuts and bolts kind of approaches. I don't know if I have a firm number for what the limits might be, but practically speaking, millimeter scale devices are going to be really, really tricky to do. That said, we can get away from that by some of the folding approaches that we have. And specifically, I didn't really say this, but the device that I showed, which is sort of this pop-up thing, which is sort of assembling itself, I would argue we could scale that down quite a bit further. These materials questions aside, in terms of fibrous materials, let's set that aside for a moment. We could scale that down quite a bit further because there's really no sort of human contact, and furthermore, there's really no friction either, because we're basing all on we put a lot of design effort into the flexures themselves, such that we're not going beyond plastic limits, et cetera. So that what you get is as close as you can get as an approximation to a pin joint, but still with a very, very low, if not negligible, friction articulated joint. So, okay, so that's one thought. But then on the other side, which I didn't say, was the amount of design effort that goes into that is tremendous. That device took, the smartest person I've ever met 6 months staring at a computer to design. And so, we've since, so we do that kind of sparingly, I guess is my point, because of the design effort that comes up. We've had some people that we've worked with try to develop some tools for automating designs and sort of abstracting out some of these low level issues of more like CAM kind of stuff. And that's been fairly successful, and that sort of lowers both the barrier to entry and to your second point about mass manufacturability. I would envision that these things would have to be, these CAM tools would have to be further developed dramatically in order to sort of get these to a sort of mass production run. We have spoken with, we've gotten to the point of speaking with manufacturing houses that build complicated electronic devices. I guess I'm not supposed to say who, but we've gotten to the point where we've had discussions with them, and it seems like a reasonable thing for them, and a reasonable capital investment on the part of some of these manufacturing houses, a couple $1 million investment to tool up their lines to be able to do this. But I think it would inevitably have to be self-assembled if we're talking about that. And self-assembled one way is the way that we buy this pop-up techniques.
Thank you.
Okay. Let's see. We have a question from Jason Wang. There you go. You should be unmuted now.
Okay. I am unmuted now. And so my question is, thank you, Dr. Wood, for presenting so many studies. But what I see here is that the current studies are focused on single robots only. What speculations do you have for if we have many of these small scale robots or soft scale robots working together, like such as self-organization, self-assembly, or like what kind of speculations do you have if we have many of these small scale robots working together? That's my question.
Yeah, that is a great question. And yes, we have not got to this because we're dealing with sort of one-off or maybe 1, 2, 3 kind of numbers here. I will give a plug for the work of my colleague Radhika Nagpal and also Daniela Roos at MIT. And there's many others, of course, who are looking into questions about reconfigurable systems, swarms of robots, et cetera, I will try to do my best not to butcher some of those thoughts, but some of the questions that come up are in more of the sort of hardware questions. How do we build them? But I guess I've sort of already given a few thoughts on that. But how to coordinate them? There's really interesting questions that come up in terms of the coordination. One of the most interesting ones to me, as somebody who's trained in electrical engineering, is the questions of what level of communication do you need? How do you implement that communication? Is that communication necessary at all? And so there's some studies that some of my colleagues have done, which has sort of explored that. And this might seem like an odd thing. Of course, they have to communicate with each other, but the energetics of communication at these small scales might be sort of comparable. The sort of energy cost per sort of, you know, whatever the metric might be per packet sent or whatever, might be comparable to the amount of energy it takes to sort of remain aloft or move about in the environment. So it's these things, again, that we take for granted for larger scale systems where the locomotion costs dominate at the energetics sort of come up. So that's one consideration is how would communication be implemented? Would it be necessary? And furthermore, you know, if you've got tens or hundreds or thousands of these things operating together, are they going to be broadcasting? Is it going to be local based communication? There's some work that Radhika Nagpal has done, which has been, you know, no global communication, only local communication, just based upon who your nearest neighbors are and who you're sort of closest to. There's questions, sort of skipping ahead a little bit, there's questions then associated with more of the sort of modeling and programming aspects. Do we think about simulating, modeling these kind of systems deterministically, or do we do it with more sort of stochastic models that are more sort of akin to chemical processes? Then there's, well, those are the main ones that come to my mind. It's not something that we are directly working on, although I see I believe a number of you that I'm looking at now are. Metin, for example, is one who I know has put a lot of thought into this for small scale systems that would aggregate for example, for operations within the human body. But those are just some thoughts off the top of my head, but it's a very ripe area. Another simple one would just be, how do you charge the things? If I've got 1,000 things that are out in the field, and they each have a battery, do they come back one by one and charge? That seems inefficient. You know, how it's very sort of practical things, again, that we might take for granted for other systems.
Very good. So we're open for further questions. Let me follow up on this charging question with the enemy of every autonomous robotic researcher, and that is batteries. And you have some particular challenges because you have to lift the batteries against gravity. So what's the outlook on that? How many orders of magnitude are you away from a robo-bee who can fly around for hours?
Well, you had me up until hours. So you know, if we relax that a bit to a couple minutes, then battery chemistries exist which will do that. I mean, we model the hell out of our you know, every aspect of the sort of drivetrain of these things. So we understand, you know, how much energy per cycle we're dumping into both reactive and real power into the actuator, et cetera, et cetera. So we know all of that. And the good news there is that it's on par with, you know, similarly scaled insects in terms of metabolic power that's being, that has been measured for those systems. The bad news is, of course, the lack of extant batteries at these scales. And so to my knowledge, there are no batteries that would be appropriate for the scales and weights that we might want, even if the battery chemistries themselves would be, you know, marginally adequate. So, you know, given the best battery chemistry, given the state of the art of battery chemistries as we understand it, we do predict, you know, a couple minutes at best case scenarios of flight. So what we've done then is, you know, nobody, and for good reason, will make us batteries at these scales because nobody else really has a use for them, at least to my knowledge. And so we had, I had a former graduate student who actually just, his name is Mishu Dududa. He actually just accepted a job at University of Toronto. He was also a battery expert. And so he made some of the first attempts in our group at actually making batteries. And there's no magic there. It's about packaging. It's about just being efficient with the packaging. As you get smaller, of course, your surface area to volume ratio increases. So you get less volume for electrolytes and more volume for packaging. And so the effective energy density goes down. And so it's sort of, you know, you're losing at all ends. But if you relax the sort of things that a mass battery manufacturer might care about, like shelf life and longevity and charge cycles and whatever, then you can cheat a little bit. And we've made demonstrations, very, very preliminary demonstrations of batteries which would come close to powering flight. So this is an active area. This is an area where we really don't want to do this ourselves. We'd love to have collaborators on this.
I'm impressed you're close, better than I would have guessed. Let's see, have a question from Junsu Kim.
Hi, I was so enjoyed the talk. I really appreciate for inspiring talk. I have a question about the power aspect. So in the case of the hard robots, we have a lot of candidates such as lithium battery motors, piezoelectric motors, and plenty of candidates. However, for the soft robots, I feel I have less choice. For example, you have shown that the hydrogen peroxide, and I have seen a recent paper that used flow batteries. However, those are so limited. So my question is, what kind of battery power system could be better or could be good for soft robots, and what aspects should be considered if I want to use for the soft robots?
This is a great question. I don't know if I have a very satisfying answer, but I mean, I think that we should be, as a community, sort of defining our goals and what would make a soft robot. I mean, if I stick a rigid battery in an otherwise soft robot, is it no longer a soft robot? And I mean, if it doesn't impact whatever the sort of main function of the system is, I would argue no. So I think that we would default, of course, to more traditional technologies. You're citing a couple of very interesting examples, like flow batteries in particular. I think I've seen a group that's, I don't think I'm making this up. I think I've seen a group that was thinking about using the electrolytes in flow batteries as also the working fluid and fluidic actuators. So, there's some clever things I think you could do with that. There's the chemistry side, there's chemical reactions. I only mentioned one. There's several other candidates that could be potentially used. Those get tricky because then you have to have the rest of the infrastructure around it, for storing fuel, valving, releasing, mediating flow, etc. So that's a potentially viable mechanism as well, but perhaps a little ways off. Another one that we've also considered, and other groups have considered, is compressed gas storage, which I think perhaps gets you further away from soft. You typically have rigid storage elements there. It's an open question, it's an interesting question, but I think I would just go back and say, I mean, if I have a soft robot, the Octobot is an extreme case, and it was more of a philosophical exploration than a particularly practical one. Although I think there are some cool innovations along the way. I wouldn't say everybody needs to stop what they're doing and replace Arduinos with microfluidic systems. That's not, we're nowhere near to that. Same thing with batteries, I think.
Thank you.
Okay, let's see, John Zhu, I see a hand up. And I'm trying to unmute.
Yeah. Okay, yeah, thank you, Prof. Robert. Yeah, very interesting and inspiring talk. So I have two questions. The first question is that for that soft robot with application in deep sea application, there are any requirement for materials? For example, the material need to sustain very high pressure or cold temperature, so which may affect the lifetime of the material. So this is the first question. Second question regarding dielectric elastomer. So without pre-stretch, so the material may extend the lifetime, but how about deformation and output force of dielectric elastomer without the pre-stretch? Thank you.
Yeah, a good question. So with respect to the materials for the deep sea stuff, we use silicone-based elastomers. Those were chosen specifically because they are impervious to the temperatures, roughly 0 degrees C temperatures at the bottom of the ocean. High hydrostatic pressures, they're fine, they're incompressible, so there's no issue there. There's no, we manufacture them very carefully so that we avoid any sort of voids or anything within the structures themselves. And we use so ignoring the hydrostatic pressure, we use an open seawater engine to sort of create differential pressure. So the absolute pressure, yes, is high from the environment, but the differential pressure inside and out is only a few psi. So so there's that I think we actually I think that's a pretty good solution. You know, going to your the second question that you had, sorry, I just blanked. The second question that you had was involved
dielectric elastomer without pre-stretch.
Yeah. So my understanding is, and I think Zhigong could do a much better job with this than me, is that the absence of pre-stretch in this particular polymer that we're using is due to the fact that it does some strain stiffening, and so it avoids some of these effects, some of these sort of pull instability effects. I don't believe. I don't know if we've really explored, done an apples to apples comparison of motions or forces that we can achieve out of these structures compared to, let's say, acrylic-based elastomers or other elastomers that have been used. The motions are relatively smaller. We're not talking about 10% strains or higher. We're talking about a few percent strain. And so I don't know if that's maybe a direct answer to your question, but you know, we're targeting sort of muscle-like properties, and so not necessarily, you know, 10, 20, 30% strain, but more in the sort of lower end.
Okay, thank you.
Let's see, we had a question from Kezi. Let me unmute you. There you go.
Thanks for the talk. That was really great. I have two questions. The first one is on the...
You're muted. Sorry.
Yeah, muted again somehow. Let me unmute. There you go. And it muted again. Yeah, it's not unmuting. I'm sorry. I don't know why. There it goes. Now you're unmuted. And you're muted again. Thank you, Zoom. Zhigang, can you take a try at this?
Okay, quick question. So two questions on the yield of successful actuators you make with the conventional hard actuators and the soft ones that you were talking about, like the multi-layer dielectric elastomers. In terms of assembly, how often do you get successful actuators between the two? And then secondly, have you thought about exploring intrinsic or extrinsic self-healing when making soft actuators to make sure that more of them are successful?
Yeah, interesting question. The yield, you know, like just thinking about like yield of our sort of actuator developments, it's not high. It's, you know, the defect, you know, particularly for the sort of soft and sort of, well, for anything sort of like fluidic actuators, those are straightforward. But for thinking about, if you're referring to the dielectric elastomer actuator, excuse me, the yield is not particularly high. The good news is that in making a multi-layer device, we can test individual layers sort of in process so that we can only use sort of the good layers. Or the good ones. So we can sort of put process controls in place to try to, you know, eliminate defects prior to making a full stack actuator, which might take many hours to assemble. But there is a lot of defects, and there's a lot of, you know, the defects that just arise from poor processing conditions and dust and contamination and all of that. And we also process the elastomers in liquid phase, so that's something where we also have to be careful of inclusions, etc. Self-healing, I haven't thought about that. I mean, that's a fascinating idea. I'm not being a polymer chemist, I'm not sure if the elastomers we have used to date would be conducive to this. They are? Okay, good. Okay. Then maybe we can, I'd love to have a conversation, you know, maybe offline about how we might be able to implement that.
Okay. Let's see, I see a question from Wengxiao Yan. And Zhigang, okay, you're good. Yep.
Yeah, hi Rob. So I'm Wenzong from UCLA with Angular Meta. So actually, I have a whole page of questions, but I think I will save some time for other people. So, but I will ask very general questions. Like, so I always talk with other people, like young researchers or maybe even senior researchers. Like, what's the most important problem for a researcher? And someone just argue with me with other reason, but I always say like ask the right answer. Ask the right question is the first and the most important thing. The reason why I argue like is that you see Rob Wu, he started from like 2004 and they start to study the flying robot, and now it's still published paper in Nature and Science. So you see, I mean, you still have maybe 20 or maybe 100 years, you're still researching the flying robots. So how does that happen? Like, and if you any suggestion for young research, how can we do the same successful path as you? Thanks.
Well, thank you. I hope I deserve at least a little bit of that. I think that we got lucky with choosing an interesting problem. I mean, I think that I tried to sort of, you know, paint some broad strokes on this, but I mean, I think that we got fortunate with respect to choosing a problem which is it's inherently multidisciplinary. It's inherently, you know, hard because of some of these, mostly because of the physical scale challenges. It's also a problem where, and maybe I wasn't explicit with this, it's a problem where there really are no off-the-shelf solutions to any aspect of this. And so that forced us to think about everything, the whole stack, ground up, every component of this, we had to think about how to develop from scratch. And so we really like problems like that. Furthermore, I think this really works well with an interdisciplinary research group with, you know, when I think about recruiting graduate students to work on some of these topics, I do feel that they have kind of like the best of both worlds. They have a large research group which is sort of focused on a particular, you know, vision in the near future, making a small robot fly, or, you know, getting a robot to go operate the bottom of the ocean, whatever. But they also have their individual thrust. You know, everybody has their own individual thing. You know, there's somebody that's working on actuators, there's somebody that's working on power systems, there's somebody working on control systems, there's somebody working on, you know, fluid mechanics, whatever. So that tends to work out quite well, and sort of seeding ideas between them also happens to work quite well. So, I mean, it's just, I can't say that I designed it, and it wasn't me, and, you know, Metin can attest to this. I mean, you know, our advisor, Ron Fearing, had this vision a long time ago, and I'm sure other people have had similar things of how can we make little things fly, for example. And you know, I just latched on to that as an interesting problem and sort of run with it ever since.
Yeah, okay, thanks.
Tang Li, I see you've got your hand up.
Okay, fantastic talk, Rob. I really enjoyed, and I think the presentations on robotics are naturally intriguing to younger kids as well, and I really like those videos you played during the talk. Definitely will recommend this recording to my kid later on. My question is related to the title of your talk on the artificial intelligence side of this. In part of the talk you covered on this experiment, you have this flying robot, right? And you have the open loop in the beginning, and then you have the setup with multiple cameras around, and then you start to record, and those will serve as the you extract the data out of it, and then serve as the for example, I assume you will have a machine learning algorithm in the back end, and those videos serves as a data extraction for the learning side of this machine. And then you the algorithm learn and feedback and do predictions, and then you help the robot to fly better. So I think the challenge in reality will be just similar like the previous discussion on the battery for the micro robot. So you want lightweight robots so they can fly longer time. To some extent, how smart or the smartness of the robot also depends on what kind of memories, chips you put on the robot, right? So that's actually the challenge. So my question is, how intensive of this surrounding setup you need for the machine learning algorithm to work currently? And eventually imagine if one of this robot or the swamp of the robots are working in the wild places, then the challenge will be, I can imagine, is how to extract those data as a learning set for the machine learning algorithm, and how fast it can process and feedback to the robot or the swamp of the robots to control for them to perform better.
Yeah, thank you for that point. I mean, a couple of thoughts on that. To get to your question about, what's sort of under the hood here, what's behind the curtain. We have what we use is an MATLAB XPC system, where we can, as control people, we can think about just drawing up Simulink models of control systems, and then this system just compiles it into a real-time executable that runs on a sort of standalone host computer. I don't know if I could quote you the specs of sort of how many floating point operations per second, or how many millions of instructions per second per milliwatt, or whatever that those have. But I will say that this is something where it's been a disconnect up until recently, meaning we've had some really, really great students come through the group who are more controls experts, and they have implemented all sorts of fascinating things, adaptive controllers, which can learn some of the sort of unknown or poorly characterized physics of the dynamics of the devices. More repetitive based controllers that can reject oscillations due to the flapping wing, and those are great. There's some real questions which I think you're highlighting of how appropriate those would be to an embedded system, and the answer is probably not very. On the flip side, the very first controls that we did, which is what basically everybody would do, is a PID controller, and that worked just fine. So I mean, it's, the difference between the flight of that system and the flight of a more fancy adaptive controller is certainly noticeable. And you can certainly do more things and more aggressive things, and you don't have to linearize about, some nominal operating point, et cetera, et cetera. But simple controllers will work. Now we're getting to this point now in some of our studies where we are surveying two things. On one side, can we come up with a metric for how computation for control is what is the metric for that? Is it just the amount of memory that's taken? Is it the memory that's taken and the clock speed and then the bit depth or whatever? What is the sort of aggregate metric for computational complexity for a given control law? And then on the other side of that, a more practical side, we are evaluating, I guess this is one place where off-the-shelf components could work reasonably well. We are evaluating off-the-shelf chip scale packages for example, ARM-based microcontrollers, and trying to see if there's a match between those two explorations.
Good. Yakov Kutsovsky.
Oh, hi, Rob. Thank you for a great inspirational talk. I think it really shows what's possible, and very hard to find actually other area where I see intersection of materials, manufacturing processes, software, kind of all coming together. My question is around applications, right? It's very interesting to follow your logic around, the soft robotics, and it's a fairly new field, and not a lot of things, kind of got commercialized yet. You look at the, soft robots, it's a great technology, but at the end of the day, it does what it does well, picking up fruits and things like that, and you showed that you can implement, catching marine life, right? Which is how to take one of the building blocks is essentially integrated into other kind of hard robotic system, right, as opposed to soft robotic system. So if you make prediction of kind of what would be the best applications, right now you have the stack of technologies and materials and all of the pieces, right? And I think this adoption is a very common adoption, right? You pick an element, it solves an important problem, and people try to integrate it. So if you look practically, how would this thing evolve? What would be your bet on which areas people will start really implementing, where technology is mature enough and developed enough to be actually usable in everyday life?
I can only give thank you for that. I can only give my opinion. I wouldn't, just caveat that I don't take any of this as correct by any stretch. But my opinion is that not precision assembly, which is where more classical robotics thrives, not, you know, moving around objects in structured environments like, you know, Amazon robotics, but more in, I believe in the manipulation side, and Rob can say much more than I can, but, you know, I think that interacting with objects which sort of fall outside of the standard sort of, you know, rectilinear and, you know, nice material, rigid properties, et cetera. And that could be in agricultural spaces, as you're alluding to, where, you know, unstructured environments, you know, a wide distribution of sizes and shapes and surface textures and all of that. I think that there's a big opportunity in more household situations, and this isn't very well refined. Not necessarily because I have a killer app for what I want to do in my house per se. You know, I can think of a few things, like I want to have, you know, make me dinner, you know, unpack my groceries and safely put my eggs in the refrigerator, whatever. Sure, but just because I think there's an opportunity where rigid robots would fail in terms of safety. So I think if we can get robots operating outside of niche examples in our homes, I think that soft robotics is a fast track to do that. What they would be doing, you know, I think we can all sort of maybe brainstorm. But
yeah, thanks. But I guess my question was probably broader than that, because you showed a lot of different building blocks. And I was actually asking about, you know, you talked about sensors, you talked about, you know, muscles, you talked about all the different things. And so I was more thinking, okay, so if I have all these, you know, elements, right, you know, manipulators will evolve their own life. And so I think they are now on the market and people will continue refine and improve them. But there are a lot of other elements which actually don't exist today. And so where would they be, you know, kind of, are they ready for the prime time, and where would they be useful?
Yeah, thank you. I don't know. Sorry if I misinterpreted that. So like, are they ready? Is one of the questions you're getting at? Yeah.
And where would they be useful, right?
Yeah. Well, where would they be useful? I mean, I think again, I go back to more like agricultural home sort of settings, and unstructured environments. You know, things where hospitals, things where safety and is needed. You know, are they ready? I mean, if you are okay with, there's some key, I think, aspects of these systems that I've shown and that other people have shown, which might make you hesitant. And those are I think, along the lines of the power and control systems, if I'm talking about fluidic actuators. So I have to have, you know, a non-trivial power and control system. And can that be made reasonably compact and cheap and reliable? Sure, but I think that's going to take some good engineering. And then, you know, if you're talking about any of the more electrically activated systems, my mind is focused on the actuation side of things. But, you know, if you can sort of get these sort of actuation voltages lower, or use more low voltage actuation, I think that would be another thing which would be a barrier that would eliminate them to be ready for more practical use. So I think that, you know, conceptually, yeah, we're ready. I think the other thing which I'm not talking about, which is also very tricky, and I'm not really even close to the expert on this, is how do we even think about modeling these? You know, I might be able to write you a controller for the systems, but that's likely going to be based upon a model for this. So how do I come up with a situation where I can have a reasonable dimensionality of a model for this that can be run in, you know, real time or reasonably fast, such that I can start to do interesting control things. So there's a few things off the top of my head that would be barriers that I think need to be addressed prior to practical use.
Great, thank you. And I think the models could be, you know, you could use machine learning models where you really wouldn't have a closed form analytical models, but you could do, you know, basically the systems which are learning as they go along.
Yep. Yep.
Okay, Metin.
Hi, Rob. It's a great talk and amazing, a lot of new developments. So I'd like to have first a question on, you know, you showed great example of passive compliance on the wing rotation, and also during robotic gripping, how passive compliance helped a lot. Could you tell us a little bit like the pros and cons of having passive compliance in the sense of design, manufacturing, and also control of any manipulation or locomotion system? Your experience on that respect would be great to know.
Thank you. Let's see, a couple of thoughts. I mean, in terms of the design, it also gets to the modeling question. For like RoboBee wings, it was fairly straightforward because it was a single sort of discrete compliances or small numbers of discrete compliances that we're talking about, not sort of a continuum of robotic system. Zhigang, did you want to say something you wanted to add?
You're muted.
He's gesticulating, so I'm
Guys, I apologize. Go ahead.
So sorry. So dealing with sort of small numbers of discrete compliances, and then coming up with sort of expressions for dynamics and parameterize them such that for example, to get the appropriate wing rotation, we have a closed form solution based upon some experimental fits, et cetera, et cetera. That's straightforward. I think that for modeling, for some of these more continuum systems, continuum soft robots, that's an open question, and that's something which that you're, at least from someone like me that sort of grew up thinking about more deterministic models. Like I didn't grow up with some of these machine learning techniques. It's my brain wants a a differential equation to describe the motion of these systems or whatever. That's something I see the field having a lot of interesting progress with, but not coming up with a sort of final final answer. Meaning, I've seen the sort of piecewise constant curvature assumptions of continuum manipulators, or piecewise smooth curvature approximations of continuum manipulators. If we can get something which would be a parameterized low dimensional model, then I don't see any problems there. In terms of in terms of sort of your point on building the systems or manufacturing systems, with compliance and how do we deal with that. I mean, I guess I don't see it too differently than more rigid systems, so long as we understand which are the sort of most sensitive parameters to sort of control for, and then designing sort of manufacturing strategies which can have good dimensional tolerancing around those critical features. On the flip side, we found that there's an opportunity with these soft systems, maybe this is obvious, to go the other direction, which is having the compliance which might define, for example, for a fluidic-driven pressurized system. Whereas, if we fully understand the geometry of these devices, we can come up with a prediction of how they might move. On the flip side, we might be able to sort of exploit sort of random defects to actually get interesting motions as well. So I don't know, I see there's opportunities in either space, to coming up with a really good model, really good framework by which we could describe the kinematics and dynamics of these soft systems would be necessary for a more classical approach towards developing these systems. But I think also perhaps you can exploit some of the interesting nuances of these soft systems, get interesting unpredicted deformation modes, etc., that could be interesting for some applications.
Thank you.
Zhigang.
Yeah, so this is a question, more general question for all three great roboticists. It's a follow-up and earlier question of Rob Howe about materials challenge. Now, just take a longer perspective, something I have some experience with. So in early 90s, I was involved with companies like Intel, like IBM, are specific materials and mechanics problem, because they are doing rapid innovation, making structures smaller and smaller. Always there's a stress problem, delamination, thermal stress, electromigration. So I was thinking, looking at the complexity you constructed and Metin constructed, it's a one of a kind. So I don't even know how to help. So even if I help with one problem, tomorrow you'll have some different problem. So seem to have a lot of difficulty. I see you guys have other difficulties. For example, Yakov just asked question, maybe these things are related, because about applications. If you don't have major application field, you cannot have industry. If you don't have industry, you don't really have generic problems for a lot of other scientists to jump in to help in fundamental way. For example, do you see yourself in 20 years develop a new type of integrated technology to do whatever robots. Is that in the card, or just everybody will do hobby level, development, one of a kind? What do you guys see in 20 years' time?
Yeah, maybe another way of I've heard my colleague Oliver Brock say, referring to some of the developments, in particular in soft robotics, as the alchemy phase of sort of this development, right? Look at all this stuff we can do, right? But to your points, what is it for? And I think there's another thing that you certainly can help with, Zhigong, which is if we do, everything that I was just describing, and I think a lot of robotics groups produce one-off demonstrations or two-off or whatever. And those are fantastic, and they prove a point, they prove a principle, they explore a phenomena, whatever. But if you were to ask me to make, 1,000 RoboBees or whatever, then these questions about that you're alluding to, not necessarily maybe electromigration, but some of these sort of the failure aspects of this, right? And how those failure aspects relate to the desired task and the manufacturing strategies, et cetera. That is something that we wouldn't be equipped to do.
Can we also comment a little bit? So I think that's a great question, and I think one thing is, of course, we are all trying to have applications that will have high impact in society and also commercially. Like I think medical applications, like both Robs are also working on medical device area. I mean, there are areas that really need miniaturization and more complex materials or mechanisms. So there, I think there are great opportunities that from just even active catheters or much smaller tools, medical tools, to more mobile untethered systems. But I think more important thing will be what will happen is with all these crazy new technologies, you will see that commercial impact will be not with the system, will be component technologies. I mean, RoboBee technology and many other great robots that we see in Rob's presentation, maybe you will not see 20 years later a high impact RoboBee maybe product, but the technologies within RoboBee might turn into a lot of other products that you could never imagine right now. So that's why our hope is not only the systems, but also the tools to create these systems that we use, also material systems that we are creating right now can have a lot of impact. I mean, we worked on climbing robots to create Gecko climbing robot, but the most impact commercially came from the Gecko adhesive itself, not the robot. So in that sense, I think as long as we are going in the very creative new technology directions, by adding more complexities, we will see both from component level and maybe even also system level, some high impact applications. At least that's my dream. I'm curious, Rob, Howe, and others, but yeah.
I agree with Metin. Yeah.
I'll take a whack too. So I tend to see robotics applications in the real world as being limited by the ability to deal with uncertainties or variability. So robots work real well in factories where there is no uncertainty, at least not in a good factory. Everything is laid out and carefully structured. And now we're starting to see the ability to move robotics into areas like warehouse distribution systems, to some extent surgery. Again, the structure of the human body is pretty well understood, pretty repeatable. And so the work that Rob outlined today, where you design the mechanics so that it performs what are traditionally thought of as sensing and control roles, greatly extends, or has the potential to greatly extend in many applications, the ability to deal with uncertainties, because now your mechanism responds mechanically to the variability in the environment. Now that said, I'm afraid it doesn't really tell Zhigong what he wants to know, which is how does that map onto materials? Because I suspect at the end of the day, that's going to be highly application specific. So the details of the robotic system that deals with surgery is going to be very different from the system that deals with warehouse distribution systems and so on. And so there's no one answer, but we are seeing now this huge exodus of robotics from the labs to real world applications. Last time I counted about a year ago, there were over 30 robotic startups around the Boston area. And so it's going to happen. So I'm afraid, Zhigong, if you want to be relevant, if you want to figure out the material's relevancy, you must go and visit each one of those 30 companies and see what they are doing and see how you map onto what they're trying to do. Sorry.
Yeah, so another aspect of my question, maybe I didn't say this clearly. So for example, when silicon technology developed for microprocessor became very mature, all of you guys know what came about were two things prominent. One is MEMS system. The other is nanotechnology. They all built on classical integration technology for microprocessors, very specific thing, right? But yet MEMS, so not everyone need to invent new MEMS material integration technology in order to do an innovative device, because there is integration technology kind of around. So right now, I don't see this happening at this moment, but you guys are creating all kinds of things. The question really is, do you see this as a path? At some point, there will be a division labor that somebody will be creative about applications. Other people will actually specialize in material integration. Do you see that's happening? Right now, it's not. Everybody is doing everything.
Yeah, I mean, I think that hopefully, so the MEMS took what, 25 years to go from lab to first commercially viable device, right? Something like that. Hopefully we can be a lot quicker than that. But I mean, I think, for us at least, maybe this is not the right way to look at it, but for us at least, we've been trying to find the killer application. Like what, to Metin's point, it's not, the RoboBee is not the killer application, but could we use this thing, this component for a surgical device or whatever. So that's what we've been looking for. And then my assumption is that at that point, if we do find that and get sufficient number of people excited, then the sort of, the shift goes to the industry.
Thank you.
Let's see, Su Lin. And my unmute button isn't working. Zhigang, once again, do you mind? There we go.
Oh, just unmuted. Hey, Rob, a very nice talk. In the first couple of slides, I learned from you that artificial intelligence is all about sensing, perception, and decision making. So you need sensors, basically. When you move from this solid robots to soft robots, you need the soft sensors. What kind of choices you have on market for these soft sensors? And do you really train these sensors for perception? For instance, our fingers are very good sensors. We touch some surfaces and we can perceive what kind of soft finishes they are, and we can make a decision based on our experience. Are we on this stage yet on soft robots?
Yeah, the perception for soft robots, I mean, it's the parallel, it's a dual of this sort of modeling question of how we would represent or how we abstract the physical structure of this in a sort of, tractable way. And obviously it'd be alleviated if we had sensors everywhere. First, in terms of the sort of component technologies that are available for these things and what's been explored, it's been mostly along the lines of like, proprioceptive type sensors, kind of what you're alluding to with skin, mostly things that are able to measure whether it's through resistance changes or piezoresistivity or capacitive changes or even optical systems or acoustic systems all embedded within soft materials. There's been a bunch of demonstrations on the ability to predict or I should say estimate self motions or contact forces. There's a lot of demonstrations of that, and they're fascinating. I don't think there's one, there's no, to my knowledge, there's no sort of standard like an IMU would be in terms of embedded system control or like more ubiquitous sensors for control and more rigid or traditional robotic systems. But there's a huge suite for things like proprioception. The other question, which I think maybe Rob has done you know, the most work in this area is how could we not just have one or two of these things, but how could we have, you know, dozens or hundreds of sensors, and what would we do with all that information? And I'm thinking of the pressure sensors that Rob had developed, which give you a very sort of large space of data. So I think, you know, I don't think it's really a question of what sensors are we going to use. It's not sensors. It's not a question of are there sensors available. It's more like, well, which one do you use for a given application, or whatever you want to sense, and then how do we, given the compliant nature of this, I can't just have one. So how am I going to aggregate sensor information? And again, it's another place where learning models come into play. I've seen a lot of interesting work where people do some training on some, you know, more sort of macro scale feature of the system and train that down into, you know, to make sense of sensor inputs.
I'll add that I think we're at a kind of jumping off point with sensing and robotics too, where the MEMS revolution, together with small high performance cameras, has made a huge difference in what's available for robots. So now you can buy a little tiny IMU for $10, has gyroscopes, magnetometer, accelerometers. It spits out high quality digital data. You interface it with a very simple standard bus. So suddenly you have all this very rich information available. And so now we can start coping with the uncertainty and the variability in the real world. And I think that's just starting to take off in robotics. Again, it's the MEMS wave had to happen, and then we can jump on it, hopefully less than 25 years later. But I see that as a huge thrust in the next, you know, decade or so in robotics.
Great.
Okay, so feel free to raise your hand, the little hand button at the bottom, if you'd like to ask a question, or we may be winding down here.
Here, do you want to ask a question?
Tingley again, yeah.
You're muted.
Oops.
As question related, I think for the microprocessing technology and the research surrounded around this area, as Zhigang mentioned, if you compare that one with robotics, it's actually quite different. For microprocessing industry and the research around that, it's actually heavily material focused, and also you have a rather well-defined purpose, right? You want to design microprocessing chips faster to deal with 0 and 1s, and it's in the very nice sweet spot that, okay, it's the driving force for many applications, and the sensors, smartphone, and all this wearable electronics, and all this robot. But I think about the robots, it's to some extent is always trying to mimic the biological species, right? Either being a human hand to grip something, or like Boston Dynamics is really trying to mimic the whole human body, or the micro robot like Robert presented today, like the flying insects, and all these biological systems and species, they are rather complicated systems. We are, even for the human body, for the insects, for the animals, their motion, how they drive the motion, how they control the motion, how they sense and form this feedback loop, are still something not fully understood. So now you are trying to mimic this system to achieve multiple functions. I think it's at a different level of difficulty over there. That's probably, you see the people in the robotics field are demonstrating all kinds of these applications at different scale, smaller scale, micro scale, even, for example, for nanoscale to macro scale. I think that's probably where the challenge, that's just my some thoughts following the discussion here.
Yeah, I think the question about bio-inspiration, like where does bio-inspiration lead us and where does it stop? And, you know, I think that's something that I've struggled with over the years. And I think the field, the robotics, you know, bio-inspired or biomimicry, whatever you want to call it, subfield of robotics, I think has evolved quite a bit. I think that, you know, the first phase was, oh, look at that cool thing, look at what it's doing, let's try to mimic, let's try to, you know, build something that does like that. I think that it's now through the influence of biologists and organismic biologists and functional morphologists has been, okay, but you got to look at the principles involved, right? Don't just mimic a structure. Figure out what it's doing, why it's doing, you know, what are the physical constraints, control constraints, whatever, to figure out why it became that way, and then emulate that, whatever that underlying principle is. So yeah, hopefully we've tried to do some more principled things along those lines.
Let's see, Tahir.
Okay. Yeah, thanks, Jigang, for giving me one more opportunity. So I just want to make a comment that, you know, for the last about 10 years or maybe a little bit less, that there's been a new wave of thinking which involves both living entities incorporated within the artificial components. So in my lab, as well as, you know, several other labs in the country, where the idea is to create biohybrid systems where actuations are done by the muscles, living muscles, as well as the controls are controlled by the neurons, but they live on an engineered scaffold. So there is an interaction between different types of cells, and they self-emerge into a self-sustained, self-assembled system. And of course, there are lots of challenges because, you know, we don't know the laws of interactions between different types of cells. And those laws may not be, the laws themselves may be emerging. And unlike, like, you know, the Navier-Stokes that remains as a law, but the input and the genetics evolve. But in this case, the laws themselves might be emerging as well. I'm curious whether systems that you have developed, this goes to both Bob's as well as Metin and many others in the audience, where there could be a vision where, you know, some of the artificial system that you have developed can be coordinated with some of the living components on it so that they talk to each other. And that's when I think a lot of intelligence can be built in. The systems may not understand in any near future, but they come up with a tremendous opportunity where, you know, 1,000 neurons or 10,000 neurons interacting with solid state systems can be talking to each other and providing intelligence at a much faster rate than putting many, many sensors. We talked about the batteries and power systems. I mean, these cells themselves are sensors, are a battery. They themselves provide all the power sources, and they're sensing power actuation. They're all built in the same volume. Whereas in the artificial systems, the battery is separate from the CPU.
Yeah.
Right. So I wonder whether we could envision a future, and this is going back to part of Jigang's question and some of the other questions, that could this broad applications and impact can be realized by making it more hybrid, biohybrid. We're not talking about bio-inspired systems, but rather biohybrid systems. And I will stop.
Yeah, that's fascinating. And it's a fascinating concept. And I'm going to just claim, I'm just going to sort of hide behind my my lack of sort of cellular biology understanding. But it's a trade-off as far as I see it, right? So you have the biological systems, the tissues that you're describing, a much greater level of integration. And that's just by virtue that self-assembly is sort of free and ubiquitous in biological systems. So you get, very interesting heterogeneous structures, et cetera, so you can solve a lot of problems at once. And that goes back to the sort of question of sort of efficiency of these materials that are involved and all of that. But yeah, the positives are very compelling, as you were describing. I guess the trade-off there is just the integration, right? With more, engineered systems. I can't really speak intelligently to that, but I can imagine that there's just maintaining while the tissue or whatever you're using is itself sort of self-sustaining, and that's over relatively short time periods, right? You still have to provide it with whatever it needs to be healthy, and the level of integration that we don't have to deal with necessarily in a sort of more engineered kind of system. But I'm sure there's many other considerations I'm not sort of thinking about, but it's a fascinating trade-off to consider. And I suspect that, depending upon the application, depending upon the use, it might just make sense to use an Arduino and a motor. But for some other things that, need to be more conducive to interacting with biological systems, or, in vivo medicine, for example, that might make a lot more sense to be thinking about hybrid systems.
Yeah, I'll jump in too. And I think this whole area of essentially active chemistry as part of robotics is something we really barely started to explore. And of course, life, if you think of living systems as chemical systems by and large, the way they do self-assembly and process energy and all that. And the potential is obvious and huge. And I think this may be one of the interesting aspects of soft robotics. We're all still looking for the killer app in soft robotics. And if everybody in robotics is working on soft robotics these days, we're not quite sure why, but it's new and it's very cool. But it may be a step towards that. If we stop working with rigid materials, maybe we can also start working with chemically active materials and take advantage of that whole sphere of capabilities in ways we haven't gotten to yet. So I think you've just explained my next NSF proposal to me. So thank you. Okay, Wen-Zhang.
Hi, Rob again. So actually, I read some paper from Professor Zhigang's group. I think it's something like a software file, and then you can control, and you can kind of invest some kind of physical intelligence into structure, something like that. And I think it's pretty similar to kind of the October. So it also includes some like kind of controlling to the mechanical structure. So I wonder, is that any kind of way to integrate them together? Because for myself, like I'm doing some origami robot, and I try to kind of invest some like physical intelligence to origami structure, something like that. Yeah, but I hadn't find a clear path to directly go through my thesis, PhD thesis. So yeah, maybe I can borrow some inspiration from you.
Yeah, I'd love to talk about the connections between all of that. Maybe we can do that offline. But I mean, the thing with the Octobot was that it was coming really from a traditional robotics engineered system, and then throwing interesting material, tricks and techniques to it. But there's probably a more organic way to do this, and I don't mean it in a chemical way. A way to incorporate desirable mechanical features, or even coming close to behaviors, without having to sort of sidestep over to an electrical engineering analogy of having a control system and a power system and an amplifier and blah blah blah. So I think there's probably better, and I don't know about the principles involved, there's probably better ways to think about incorporating a desired motion behaviors or whatever within mechanical systems. I'm happy to talk to you offline about that.
Yeah, okay, thanks. If nobody else, I will continue. Yeah, sorry. So actually, I'm always thinking about the robot bee. So I mean, the robot bee now is kind of like centimeter scale, right? And I just wonder, like, because there are lots of like flying insects, they can kind of 1 millimeter maybe. So I just wonder, like, is that possible to maybe scale down a little bit for that, maybe for special like application, something like spiring, something.
Yeah, we can scale down. I mean, the components and techniques that we use, we could scale down by maybe another factor of 10 in mass. So, whatever that would be in terms of physical scale. But beyond that, we run into some challenges with the use of these sort of fiber-based materials. We're limited in the thicknesses of materials that we can get down to some discrete values, etc. So there's some practical constraints on that. The principles involved, I mean, you're you're messing with the fluid mechanics, which you're talking about just the flapping wing devices, of course, and that becomes something you need to pay attention to in terms of your designs. But just in terms of building something, you know, isometrically scaling it down, you know, we could go smaller.
Great. So Rob and Rob, are we winding down? Right. Thank you so much, both of you, for staying long and interacting with people. I certainly get much better appreciation of the scope, the challenge you guys face, and opportunities you guys create. So let's talk more. Rob and I have spending lunch together. Rob Howe. I should spend some lunch together with Rob Wood as well.
Please, I would love that.
All right. How about we clap hands? Thank you.
Thank you. Thank you.
All right. Bye.
Thank you, everybody. Thanks, Shikan.
All right.